Everyone, my name is Ivan, and our topic today is moving Apache Ignite into production, best practices for distributed transactions. It's the second part of my Ignite consistency webinar series. The previous one was easy. It was overall overview of consistency guarantees in Ignite. And today we will dive much more deeper exactly into distributed transactions in Ignite. So a few words about myself. I'm leading the data consistency development team in GridGain systems. I'm also an Apache Ignite committer, and I have performed several major commits to transactional subsystem. And actually, what we will be discussing today is mode, which you can specify for every Ignite cache. You can pass transactional to cache atomistic mode, and thus all your operations that use this cache will be transactional. This gives you an option to do transactions which are cross-partition. You can access several partition, also cross-cache, multi-record, multi-node. So it's complete distributed transactions. It can span any amount of data that you want. Transactions give you full ACID guarantees. It means all updates that you made inside the transaction will be consistent and atomic. Either all of them will be applied or neither. And transactions are failover safe, meaning that ACID is still guaranteed if some of participant nodes fail. Let's go through today's agenda. We'll start with a brief overview of transactional subsystem API. I'll cover all methods that I consider more or less important and applicable for production use. Next, we'll proceed to isolation and concurrency. These two parameters can be set for every transaction, and exactly those parameters are the configuration for the consistency and concurrency guarantees that you want exactly for your specific transaction. We will cover some use cases, and I will explain the differences between those guarantees. Third part is exactly about diving deeper into the transactions world. We will check what happens under the hood of transactional subsystem. We'll talk about two-phase commit protocol and overall transactions flow between the nodes, and also we'll discuss how transactions recover themselves if some participant nodes fail. The last section is more practical. It's about moving safely into production. I had some experience of moving transactions into production deployments, and I have bumped into several corner cases, and I will share some recommendations how to deal with transactions to avoid blockings, stop the roll pauses, contentions, etc., as much as possible. And the latest part of last section will be about troubleshooting. We will check some log messages or monitoring instruments in order which can be useful in order to debug and understand bottlenecks into your transactionals code. Well, let's proceed to API overview. I will briefly describe the most common methods in transactions API. Probably you are already aware of them, but anyway. Entry point to transactions API is ignite.transactions call, and it gives you instance of Ignite transactions interface, which is actually main facade for transactions API. On this Ignite transactions, probably the most important method is transaction start, which accepts 4 parameters. It actually starts a transaction, and you can configure concurrency and isolation. We will discuss these two later. Timeouts, which is crucial. I recommend to use timeout for every transaction. And if you have specified some timeout that is different from 0, transaction will be automatically rolled back by the system after this specified period. Transaction size is quite optional. You can always pass 0 to the transactional size, but if you're sure in advance which number of entries you will affect inside the transaction, you can pass this number of entries, and this may very slightly increase your performance. When we call transaction start, transaction is actually started and is attached to the current thread. Thread is important here because all cache operations that are executed in the current thread will be within the transaction in case this operation work with transactional caches. So here's the example. We just perform a transaction start. Right now, this thread works in transactional scope, and these two operations, put and remove, will be transactional. So either both of them will be committed, or the whole transaction will be rolled back. Yes, and another probably not so likely to be used in real code but handy method is transactions.tx. According to the fact that transaction is attached to the current thread, you can just execute transaction.tx and it will return the transaction instance that is attached to the current thread in the moment. It can be useful. You may consider transaction as a thread local variable and perform something like this. You can open a transaction, call some method, and probably method inside the method, and inside the latest method, you can acquire your current transaction and do some operations with your transaction. So there's no need to pass transaction instance directly through the whole stack trace. And the second most important method is transaction commit. When you call commit, your transaction is started to perform two-phase commit protocol, and you have to know that data is not changed unless commit is called. So here's the example when commits in the end of transactional scope will cause actual commit and data update. And if you didn't call commit, your transaction wouldn't be committed anywhere. So no data will be updated even though you have called some puts or removes into your transactional scope. So you have to call commit always. Implicit method, which also is not likely to be called in code, but it's always called, is transaction close. When we call close, transaction gets detached from the current thread, and if transaction wasn't committed, it gets rolled back. It's actually called every time when we end the try block in initializer section of which we have started the transaction. So a transaction is auto-closable, and when this try block is ended, close is called. And in this example, commit wasn't called, so after the end of try block, this transaction will be rolled back. And a few words about rolling back transactions. Actually, there are two ways to do it. First one is probably more common, especially in SQL world, set rollback only. When we execute this method, transaction can still operate. You can still add data to your transaction, but after this call, the only possible outcome of the transaction will be rollback. It's just sets marker, and when we call commit, this marker is checked and transaction is not proceeding to the commit stage. This method is reasonable to be called only if it's called before commit. If it's called after the commit, so commit has already started, and this method will not change the state of the transaction. Another way to roll back the transaction is calling rollback method. It has different semantics. It's much more greedy because it performs greedy and synchronous transaction rollback. This method blocks until the transaction is rolled back, and rollback is started immediately. Well, let's proceed. Another one which is not likely to be called in business code, but still there's an implicit method, and it will return true if the transaction was started implicitly. By implicitly here I mean that it started without tx start. Here's the example. If you perform a put all to your transactional cache, this call will actually start implicit transaction, and if you will gain or obtain instance of the corresponding transaction, its implicit call on this transaction will return true. Otherwise, if it was started directly, you will get false. Another one handy mechanism in transactions is suspending and resuming the transactions. So as you know, transactions are attached to the thread. And in some cases, for example, if you have complex architecture of your business app that works with Ignite and embedded mode, you may want to, for example, assemble different parts of your large transactional batch in different threads. For example, if you use something like fork join pool and every subtask may add something to the transaction or something like this. You may call suspend method, and after suspend method is called, transaction gets detached from the current thread, but after it's detached, it can be resumed by calling the resume method, which will attach only the suspended transaction to the current thread. And after this, you may return transaction execution and add some more data inside the transaction. So here's the example of how it can be used. You may start transaction in one thread, call suspend, probably submit an asynchronous task somewhere, and later another thread from the pool can pick up this activity, resume the transaction, add some more data probably, and perform a commit at last. For every transaction, there is always a state. Transaction is always in some or another state. I will not explain every state in details. I will keep this table only for reference. If you are interested, you may check it later in slides. Later in under the hood section, we will go through the transaction flow, and I will describe from which state to which transaction goes on different stages of transaction commit. And here's the state machine of states. Here, if you see an arrow, transaction can be transferred from one state to another. So for example, from active state, which is starting state for transaction and can be prepared and committed, then it's different parts of two-phase commit protocol. It can be suspended and then returned to active. It can be rolled back, and if it gets rolled back, the only possible outcome is final rollback state. I will keep this picture for reference as well. And the last point about transactions API are exceptions. If you work with transactions, if you write codes that uses Ignite Transactions API, you need to be sure to handle some exceptions. There are 5 most common of them. Let's go through it. First one is transaction rollback exception. It will happen on automatic transaction rollback when system has decided for one reason or for another that transaction should be rolled back. You will get this exception on commit attempt. The next one is transaction timeout exception. Probably it's more obvious if you have specified the timeout for your transaction. Then when this timeout point has come, you will definitely get this exception in attempt to continue using your transaction after the timeout. Transaction deadlock exception also explains itself. If you have introduced key level deadlock with several concurrent transactions, you will get this exception with details on what exactly was the reason of deadlock. Transaction optimistic exception is a more specific one. It's applicable to only one special isolation concurrency pair. It's applicable for optimistic serializable transactions. We will discuss them in details a bit later, but the interesting point about optimistic serializable transactions is that locks in those transactions are optimistic. We don't actually lock an entry, we just check the current version, and on commit we will compare this version to actual version. So we just take the version and optimistically rely on possibility that no one else will touch this entry. So if this optimism if our optimism was premature and one of entries was touched by another transaction, commit attempt will result in transaction optimistic exception. And the last one is cluster topology exception. if one of primary nodes that keeps data that is affected by your transaction fails, you will get this cluster topology exception, which is a signal that you should retry your transaction on new topology. Well, I think that's it with the API. Let's go a bit deeper and discover isolation concurrency modes, use cases for each, and differences between those modes. I will repeat myself a bit from my previous presentation. Optimistic rate committed modes is the one with the weakest guarantees. The most common use case for it is atomic batch update. You can start optimistic rate committed transaction, for example, perform some put all operation and commit your transaction, and what you will get is ACID guarantees. So your whole batch will be committed atomically. It's equal to just calling transactional cache.putall batch. It will start implicit optimistic rate committed transaction, but this one is more flexible. You can perform more complex operation like put some entries and remove some entries, and then when you decide something, put some more entries, and total and all entries affected by your whole transaction will be committed atomically like the single batch. The one with this a bit strongest guarantees is pessimistic rate committed mode. In this mode, we acquire pessimistic locks on every entry that we write. So good use case is exclusive update. Imagine that you have users, and from time to time you want to perform complex operations with those users. You want to, for example, update transfers cache, update audit cache, update some more caches that are related to this user. But you want these operations to be performed exclusively for every user. So you don't want two concurrent transactions to work with the same user simultaneously. In such case, you may create a last user execution cache for synchronization. You may put at the start of your transaction something with the key that is directly mapped to your user. And after this put is successful, you have acquired an exclusive lock to this key. So after this, you may perform anything you want with your user in another caches. And if there are lots of these operations in your business codes which follow the same pattern, they acquire exclusive lock for user by accessing last user execution cache at the start. You will gain the semantics where it will work like mutex on this user, because once this lock is acquired, you may work exclusively on this user, and if someone else is working, you will just hang on this line until the lock will be released and your transaction will be able to proceed with the user. Next point is probably the most classical one in transactional world. It's safe payment processing. You may achieve this with pessimistic repeatable read modes, and this is true because exclusive locks are acquired not only on writes but on reads. So what you need to do is just query current balances of accounts. You may credit one account and debit another account for the same amount, then perform puts. And after these operations, exclusive locks for both account 1 and account 2 acquired. And this way you may be sure that after such transactions, your total amount of money in your system will remain unchanged. A few words about snapshot isolation. In the world of the databases, snapshot isolation is a guarantee that all reads made in a transaction will see a consistent snapshot of the database. A quick disclaimer that snapshot isolation itself isn't possible in Ignite transactions. It's kind of possible in multi-version concurrency control modes, which is available since version 2.7, but it's still in beta. It's not recommended for production use, unlike regular Ignite transactions, which are totally stable and recommended for production use. And good news here is that snapshot isolation is possible to be emulated. Of course, it depends on your case and what type of locks do you want to acquire. But here I'll share an example when we may get something like snapshot isolation behavior. And this is possible with optimistic serializable transactions. Let's consider a scenario where you write something like a social app, and you have a lot of users from different cities, and in every city you want to motivate the most active user, which does the best for your business success, and you want to assign an ambassador status to this user. And what you want to be sure that only one user can be an ambassador in each city. So what you can do here is start an optimistic serializable transaction, perform a get all operation, which will query all users that are residents in your city. And after this operation, as you know that locks on reads are acquired starting from repeatable read mode, and serializable is even stronger. And in such case, optimistic shared lock will be acquired for all users. Two keywords here as that they are optimistic, meaning that no real locks will be acquired. Transaction will just query the version of the corresponding keys, and commit will fail if this version has changed. And shared, so several optimistic transactions can acquire optimistic locks on the same keys, and in case those keys are just those locks are just acquired for read, not for write, those transactions can be committed without a conflict, just like multi-version concurrency control should work. And after you have acquired optimistic shared locks, you can perform code that will calculate an ambassador. So after this operation, reads will be repeatable, so you can safely scan through your map and calculate a user that should be an ambassador. And then you can perform transaction commits, and this commit either will fail in case some user will be changed by concurrent transaction, but in case your optimism so in case your optimistic assumption was successful, your transaction will be successfully committed in case no one else has touched none of the users from your city. And successful commit guarantees that only one user from city will be promoted to the ambassador, because in this transaction we have queried all users and none of them were ambassador. We assigned an ambassador status to one of them, and success of the commit means that no one else has assigned or changed any other user. So of course it's not a true snapshot isolation, because you can acquire predicate or range locks. But anyway, this is a way that performs well, because it can give you good concurrency guarantees, because no real locks are acquired. Well, so here's the comparison of 4 modes that I have reviewed. There are actually no more modes in Ignite transactions. Actually, there are 2 values here, optimistic and pessimistic, and 3 values here. In total, there are 6 pairs, but 2 of pairs are equal to the previous ones. So optimistic read committed gives you ACID guarantees, but locks are acquired neither on writes nor on read. Pessimistic read committed assumes that locks are acquired on write. Pessimistic repeatable read implies that locks are acquired on both write and read, which makes safe payments processing possible. And optimistic serializable in terms of guarantees is equal to pessimistic repeatable read, so you can perform safe payments processing with optimistic serializable as well, but it just differently operates with locks. Instead of acquiring real exclusive locks like pessimistic repeatable read transactions do, optimistic serializable transactions acquire optimistic locks, and which of course implies that your transaction may fail with transaction optimistic exception in case your optimism was premature. The good point about optimistic serializable transactions is that they are totally deadlock free. You can access the keys in reverse order in concurrent transaction in repeatable read pessimistic mode and get yourself into the deadlock, but it's totally impossible in optimistic serializable mode. your deadlock transactions will be just rolled back with transactional optimistic exception. So those two are the same, but they are different in terms of locks and concurrency guarantees. Well, let's proceed to the third part. I think it will be the hardest. We'll check what happens under the hood of transactional engine. Yes, we'll start with transaction flow. We will consider scenario with its several client and server nodes involved, and we'll consider an example transaction, and I will see how data flows between Ignite nodes and how the state of the transaction is changed. So here's the example. What happens here is that we have 4 server nodes. There are 2 primary nodes that will actually keep the primary versions of the keys that will be affected in the transaction. There are backup nodes, which every one of them maps to the corresponding primary. And there's client nodes, and client node joins the cluster and wants to update some data inside the transaction. So according to next to each node, there's a table. There are 4 entries in this table. First one is transaction state. This one is enlisted entries. By enlisted, I mean that this node keeps actual pair of key and value. So if value is enlisted, node actually keeps the data that is affected by transaction. Locked keys means that there are exclusive key locks acquired on this node and written write ahead log or written while there will be something when data will be actually updated inside the transaction and written to the storage and to the write ahead log. So everything starts with transaction start call. At this point, there's active state on client node, and another nodes are totally unaware of the transaction. Client invokes cache puts. This entry gets enlisted into the transaction, and at this point, other nodes are still unaware, but if we work on pessimistic repeatability modes, this operation should acquire an exclusive lock. So we go to the corresponding primary with lock requests. Primary knows about the transaction from this point. It turns to the active state, and after the lock is successful, primary responds to the client with lock response, and after key is successfully locked, this operation is unblocked. So before lock response, client thread was hanging on this call, and after we have received lock response, it's unlocked. You have to know that entries only enlisted on initiator node or on clients. Primary is aware of the lock, but it still doesn't contain any data. It still doesn't contain the value. Next, puts will go to another primary, and the scenario will repeat. We will send lock request. Transaction will go to active state. Key will be locked, and lock response will unblock the operation on the client. Interesting part happens when we execute the commit operation, which should actually update the data. And here is exactly the start of two-phase commit protocol. It's called two-phase because on the first phase, we acquire all locks on all participant nodes, including primary and backups. And after these locks are acquired, we proceed to the commit phase, on which data is actually written to the data storage. So commit starts with preparing. Transaction, when we invoke commit, goes from active state to preparing states on client, and client nodes start to distribute prepare requests to primary nodes. They turn the transaction to preparing state as well and delegate those requests to backup nodes. And at this point, entries are enlisted on both primary and backup. So only on commit phase, data is actually distributed across the whole node, transaction participant. And all nodes, including primary and backups, have the corresponding keys locked. So both primary and both backup has unique locks to the corresponding keys. Backup responds to their primaries on the successful prepare. Primaries respond to coordinator node on the successful prepare, and at this point, transaction goes from preparing state to prepared state on every node. And this is point of no return after this, after the fact that transaction is prepared on all nodes. We execute the second part of two-phase commit protocol, and transaction on clients proceeds to committing state, and it distributes commit requests to primaries. When primaries receive commit requests, they unlock the keys, and with unlocking, they actually write updates to the write headlock and to the storage. So exactly this is the point when data that you have affected inside the transactions are written to your data storage. Primaries write data and they get requests to backups. They as well proceed to committing states, release the locks and write updates to the storage and write a headlock. After that, they respond to primary about successful commit. Primaries respond to clients with successful commit, and transaction gets committed. Transaction state on client turns into committed state, as well as on all other participants. And only after this, this call, which is executed by thread on client node, is unlocked. So commit returns control to the thread that has called it only after transaction was committed on the whole set of participant nodes. That's it. Here's the reference of what I just explained. You may check it after the presentation if you want. And another interesting fact about transactions, which is very crucial to know about before going in production, is transactions interaction with partition map exchange. Partition map exchange itself is a distributed partition state consolidation protocol that is triggered on every topology change. Today, I will not explain in details what is actually partition map exchange. Here's a short description. If you are interested, you may check excellent partition map exchange under the hood article on Apache Ignite wiki. And how it interacts with transaction is the fact that partition map exchange, when it happens, inflicts short stop the world pause on all transactions, on all parts of the user load. And here is why it happens. To explain why it happens, I also to share some words about mapping the transaction. So here's another example. There are two clients. There are three primary nodes. Let's consider that there are no backups. And client node starts a transaction. It performs put. And on every access to primary nodes, it happens on first lock if you're using pessimistic transaction, or on commit if you're using optimistic transaction. Transaction gets mapped to the specific topology version. Topology version is a vector that is increased every time when topology is changed, and every increase introduces a partition map exchange procedure. So when we firstly access primary node, this transaction will be mapped to the topology version 2.0, and after this, transaction may be finished and will proceed only on the version 2.0. When this happens, let's consider a bad scenario where one of primaries fail. Fail of one of the primaries changes topology version to 3.0, and it starts partition map exchange procedure. And partition map exchange procedure can't start while there are still active transactions, because it's a consolidation protocol of partition states, and partition state is not final while there is still transaction that may update some data. So partition map exchange await for this transaction. In turn, partition map exchange is distributed process, and all nodes will wait for end of partition map exchange on the slowest node. So partition map exchange on this node is blocked by this node, which is in turn waits for this transaction. And in case another client will start next transaction after the topology change, it will be mapped on its first put on topology version 3.0. And the bad news here is that transaction actually can start working until the partition map exchange to version 3.0 is finished. And this is true according to the fact that after partition map exchange, we calculate final partition distribution, and transactions should know on which node it should go in order to perform exclusive lock of the keys or to perform a commit. So transaction is mapped to 3.0, this transaction is mapped to 2.0, this transaction waits for partition map exchange, and partition map exchange in turn waits for this node, which is in turn waits for this transaction. Consequences of this is that when there's one long transaction and partition map exchange starts, if your topology changes, the following transactions will wait for this whole procedure. So transactions are kind of vulnerable to topology changes. They are, of course, still be operating, but you may experience some latency increase when your topology is changed. So to sum it up, partition map exchange is triggered every time when topology changes. Partition map exchange to version X can finish if there are transactions mapped to version Y that is less than X, and transactions can't map to topology version X if partition map exchange that is linked to version X is not finished. So here's the caution that partition map exchange, while long transactions are in progress, will freeze all successive transactions. It will freeze them until the whole exchange procedure is completed. It's not a blocker to go to production. There are ways to tune your cluster to mitigate the consequences of this architecture detail. I will tell you about them in the last section of my webinar. And also, when we are still under the hood, a few words about transactions recovery. Transactions recovery is a safe transaction finish protocol that is used if a coordinator node or a primary node will fail. And let's check the same example. Imagine a situation when we in the middle of transactions commit. So commit is executed on client node, and client has distributed prepare request to all nodes, including primaries and backups. It also has started to commit a transaction, but right now, for some reason, it fails. And this is strange because in a normal flow, nodes await responses from transaction coordinator, especially primary nodes. And right now, there's no node to await response from. That's no problem. Every node that has some active transactions listen for discovery events, and nodes will find out that transaction initiator node has left the cluster. At this point, they'll start a recovery procedure. Transaction recovery feature will be initiated on every node, and all participant nodes will exchange their current transaction state and reach a consensus on which should be done with the transaction. So in this example, on every participant node, transaction is in prepared state, and if transaction is at least prepared on all participants, in this condition, transaction will be committed because safe commit is possible. Let's change scenario a bit. Imagine that transaction is prepared on chain of one primary and backup nodes, for example, on one key, and it's still active on the second key because a client before it has left the grid didn't succeed to send message to this subset of participants. In such case, nodes will exchange their states and they will reach a consensus that transaction is not prepared on some participants. So it means that no data is updated anywhere because data starts to be updated only on second part of two-phase commit protocol, which takes place only after the transaction is prepared everywhere. And at this point, safe rollback is possible and transaction will be rolled back. Here's the reference, and this logic, according to recovery, is safe because there are two invariants. First of them is if transaction has changed data somewhere, then transaction is at least prepared is least prepared or above. Above means committing or committed on all nodes. This invariant implies from the two-phase commit protocol, and two-phase commit protocol in turn starts actual data updates only after that transaction is prepared everywhere. Second invariant is if transaction is below prepared somewhere, transaction still hasn't changed data anywhere, and this invariant also implies from the two-phase commit protocol. So according to those invariants, we either roll back transaction safely or commit the transaction safely. Well, let's it with under the hood. Let's proceed to the last section about the most practical section. It's the tips for moving safely into production if you use Ignite transactions. I will I will discover several most known pitfalls that we have experienced when we were deploying Ignite transactions into several production use cases. Well, the first one is key contention. By key contention, I mean that key locks are exclusive, and if in case your business code has concurrent transactions that access the same key, they will just line up on this key. So consider an example where you have several concurrent transactions. Each of them accesses or writes some hotkey, and after these transactions perform another action. And in case of such codes, there will be strict happen before relationship between action 1 and action 2, because action 2 can't start until this hotkey is locked, and it will not be locked until this transaction will be committed, and this transaction will not be committed until action 1 is finished. So there is strict happen before chain, and all this action 1, action 2, action 10, etc. will be executed by turn. There will be strict order between them, and this may imply increase in transaction latency and increase and the total short stop of the world in case of partition map exchange. Next pitfall is executing really heavy activities inside the transaction. So here's example which we have also faced. Some users tend to start the transactions, get some locks, and then execute call to some external slow service. Go to Kafka, do something else, do something heavy, go to another database, etc., etc. If they do this during this operation, keys and topology will be locked. It's okay, but if this operation is really slow, they will be locked for the whole time of this slow call. It also means that dependent loads, which, for example, want to acquire locks on the same key, will freeze for the whole duration of this long call. And in case of so-known partition map exchange, all of the load will freeze for the duration of this slow call. There is always such a risk. Another pitfall is key level deadlock. Let's consider this example. There are several threads that perform pessimistic repeatability transactions, and they access the keys in different order. So if you have transactions like this executed concurrently, there's a risk of the deadlock, because if one transaction will acquire lock for key 1 and another for key 2, there is a classical example of deadlock, and there's a cycle in wait for graph. Yes, there's definitely deadlock risk. And enough with bad news. Right now, we'll discuss how to avoid these pitfalls. The very common and probably the most important advice for all scenarios when you work with transaction is using timeouts. It's strictly advised for production use to specify a timeout for your transactions. If it's not convenient to specify timeout explicitly in every transaction start call, you can specify default timeout, and it will be applied for transactions that do not have an explicit timeout specification. Another option is setting a shorter timeout in case of partition map exchange. For example, you may specify 5 seconds timeout as a default timeout and 100 milliseconds as a timeout in case of partition map exchange. So in regular life of your cluster, your keys will be locked for maximum 5 seconds, but if partition map exchange will start and stop of the world pause will be started, then timeout will be instantly decreased, and after, for example, 100 milliseconds, your transaction will be rolled back. So you may get a bunch of rollback exceptions in case of partition map exchange, and then after it is finished, your cluster will operate just as before with the regular 5 seconds timeout. So with these two, with these timeout options, you will deal you will work around the key contention case, the heavy activities inside the transaction case, and those will be worked around by just rolling back your long transactions. And regarding avoiding deadlocks, yes, timeout is also important because Ignite has internal deadlock detection mechanism, but it's triggered only on timeout for performance reasons. In case you haven't specified a timeout for your transaction, deadlock, if it has happened, will not be detected. Good advice for avoiding deadlocks is preserving global order of keys access. So don't write code like this, but sometimes accessing keys in reverse order can be not so obvious. For example, if you perform a put-all operation and you pass a hash map to the put-all methods, order of iteration over the hash map is not determined, and you may do concurrent transactions that perform put-all of the same set of the entries, but if you use hash map, iteration order will be somehow changed, and there will be a pair or set of keys which will cause a cycle in wait for logs graph. Good practice here is using ordered collections or ordered maps in put-all method. So you can just pass a tree map, for example, to the put-all, and you will never get into deadlock. And with when none of those two described options is possible, you can always use optimistic serializable mode, because in this mode, deadlock is never possible, and you can use optimistic serializable just as last resort option. When you are already in production with transactions, you may discover your pitfall situations, which we have discussed by reading logs. So, for example, if some transaction is performing for too long period, you may find a report that looks like first k long running transactions. You will see detailed info about your transactions, and you may configure even a monitoring that if this message appears in logs, there's some kind of problem with your transactional load. Another one is the deadlock detection analysis results. When you bumped into key level deadlock and your transactions will be are successfully rolled back by timeout, in logs you will see detailed report about which transactions were deadlock participants and which keys participating in this deadlock. You may also monitor this message and make some decisions, probably about changing your business code in order to avoid those deadlocks. Specifically for case when your transaction may occasionally perform a long call to external service in transactional scope, there's a monitoring that in case there's a long-running transaction, it sends a request to the transaction's owner node, which dumps its stack trace, and in server log you may find this message, dumping the near node thread that started transaction if transaction is long, and here's the stack trace of the transaction owner thread. So in case you really perform some call to external slow service, you will see this exactly call in this stack trace. You can also monitor this and make some decisions about probably excluding your long calls outside of the transactional scope. And if the worst situation that is possible with transaction has happened, if your long transactions exists at the time when partition map exchange is in progress, and if it took a long time, you may find this message in logs: failed to wait for partition release feature. It may sound strange, but presence of this message in logs is a direct signal direct signal on the fact that partition map exchange procedure can be finished because of the some transaction or because of some user load that is still in progress. And below that failed to wait for partition release feature, there will be an information about transactions that are currently pending, and you may analyze this information and also be aware that something is wrong with your transactions usage. Yes, and another modern way to monitor and analyze your transactions, not only troubleshoot, but probably to make some decisions according to performance, is transactions tracing. It's coming soon. It's already released in GridGain in release 8.7.19, and it's likely to be released in Ignite 2.9. So Ignite works with distributed tracing. It reports activity on all nodes as open census spans to the external tracing system. We use open tracing here. Tracing allows to trace the complete transaction flow. So if you're interested to improve performance of your transaction, you may, according to the traces, you may understand especially which part of the transaction was slow. Probably it was write to the storage, or it was acquiring locks, or something else. You will get all this information. And when tracing will be released, there will be an option to enable tracing of transactions selectively by a so-known transaction label. So you may decorate your Ignite transactions instance with label call, and every transaction that will be started with decorated Ignite transactions will have this label. For example, all your business code that is related to end of day clearing, I don't know, may be marked with this label, and then you may configure tracing to trace only specific transactions that has this label. It will look something like this. There will be overall set of collected traces, and for every transaction there will be a distributed tree, and for every operation there will be a duration, and every operation probably and some operations produces more child operations. So here's the example when transactions has started. It has started to map to the topology. It has started to acquire some locks. It has started to enlist some entries, and so on. And you may see total transaction flow from transaction start to transactions commit. Consider using it if you want to know more about transactions or want to optimize your performance. Well, here's a bit of reference according to the tracing. There's an Ignite Exchange proposal in Ignite Wiki, and there's a documentation on tracing on GridGain developers portal. You may check these links in slides if you are interested. And I think that's all I wanted to say today. Thanks all for your attention, and now I'm ready to answer your questions.
All right, time for questions. Ivan, the first question I have is about deadlocks. In the case of deadlocks, after the timeout, which transactions persist and which transaction would be rolled back?
Well, in case of deadlock, the only possible outcome is a rollback of all participants, of all transactions that participate in deadlock, because neither of them is able to acquire locks on all keys, and this is necessary to start commit. Commit is not possible until we have acquired locks for all keys that we have touched inside the transaction.
Great. The next question we have is about having lots of entries in a map. So we have hundreds of entries in a map, and the commits seem to take unreasonably long. Any insights?
Yes, it depends. From my experience, there are two main reasons for performance degradation of transactions. It's either waiting for locks for some entries on your map, or perhaps it's slow performance of actual data storage writes. In case of slow locks, your transaction hangs until it can acquire all keys, can acquire exclusive locks on all keys, and if there are concurrent transactions in your system that work, and each of them work with big map, so all dependent transactions, by dependent I mean the transactions that work with keys that are already touched by another concurrent transactions, all these transactions will line up because there's exactly a key contention scenario. In such case, in such case, the contention on key locks is reason, and you may consider splitting your transactions into slower transactions, or probably debugging and finding hotkeys and probably changing your code in order to remove the number of hotkeys. In case the commit is the reason, so commit takes place when all locks are acquired, so there is no problem with key contention, but probably if your storage is slow, I had an experience that commits are slow when you use network, when you use virtual disk, so you don't have actual persistent storage on the node, but you have mounted network directory, and I experienced that latency when you access a remote storage can be really high. So this is possible. This is the second possible reason of transactions performance degradation. How to determine which of the problems is the reason? Well, you can take several thread dumps. There are more advanced commands in control sh, like there is cache -- contention commands, where you may specify length of the queue, and it will dump all keys on which there's a long queue. Or you can wait for tracing and trace your transactions, and according to the traces, you will be able to discover whether locks phase or commit phase was slow.
Great. I think we have a couple of other questions to go. One question is, if we aren't using explicit transactions, do you see value in scraping logs for long-running transactions?
Okay, just once again, if you're using explicit transactions,
if you aren't, like for implicit transactions.
Okay, yeah, if you're using implicit transactions, yes, still if there are some problems with logs or something else, you will be able to monitor logs for long running transactions, because implicit transactions are just like the regular transactions, they have just implicit flags set to true. So yes, implicit transactions can be monitored in long running transactions reports or any other reports that I mentioned.
Awesome. And then the last question is, can you clarify the behavior of transactions when a timeout is not specified explicitly? Is there a default timeout?
No, there is no default timeout so far. A default timeout is 0, meaning that there's no timeout by default. And yes, by default, if you will bump into the deadlock, you may hang in this deadlock forever. So that's why I strictly recommend to use timeouts and specify default timeouts. And basically, I started a dev list thread, and there's already Ignite ticket created to change default timeout of transactions to 5 minutes. So yes, this is the first thing that you should do when you go to production, specify default timeout.
All right, great. We are out of time. Thank you. That brings us to the end of the Q&A section and to the end of the webinar. Audience, as I had mentioned, we had recorded today's session, and we'll send an email out with a link to the recording. Okay, thanks, Ivan. Thanks, everyone. Have a good day.
Thank you.